Welcome to the Explainer. Today, we're tackling something pretty mind-blowing: how the abstract mind of software actually transforms into the physical body of hardware computation. We are going to completely demystify how logic takes physical form. Here's our agenda for today. 1. Software meets physical hardware. 2. The 4 basic logic gates. 3. Tracing logic circuits. 4. Adding bits, the half adder. 5. Adding more, the full adder. And 6. Scaling up to CPUs.
Section 1. Software meets physical hardware.
Up until now, you might have thought of Boolean logic, like evaluating A and B, as something that lives totally in software. And sure, your Python code is kind of like abstract thought. But in reality, those exact same algebraic rules govern physical hardware. Every and, or not you type directly maps to a tiny electronic circuit inside your chip. And these physical circuits literally use voltages to represent data. 0 volts usually means logic 0 or false, while 3.3 or 5 volts represents logic 1 or true. So Boolean algebra is the literal bridge between the code you write and the physical electrons zipping through your machine.
Section 2. The 4 basic logic gates.
So what is a logic gate really? Simply put, it's an electronic circuit built out of transistors that computes one specific Boolean function on its binary inputs. It takes in one or more binary signals, processes them, and spits out a single binary output based on a strict mathematical rule. They are basically the absolute simplest decision makers in a computer. Here we have our big 4. You're probably familiar with and, or, and not from writing code. The AND gate only outputs a 1 if all its inputs are 1. The OR gate outputs a 1 if any input is 1, and the NOT gate just completely flips the input. But pay close attention to that last one. There's a crucial 4th gate we absolutely need for arithmetic, and that's XOR, or exclusive OR. Notice the fundamental difference between standard OR and exclusive OR. With a standard OR gate, if both inputs are 1, the output is still 1. But XOR operates under a strict rule: one or the other, but not both. If both inputs are the same, either both 0 or both 1, the XOR gate outputs is 0. It only gives you a 1 when the inputs differ. This specific quirk is going to be a real game changer when we start talking about binary addition in just a minute.
Section 3. Tracing logic circuits.
If we want to mentally walk through a circuit, which, by the way, is a core skill heavily tested on the AP exam, we use forward tracing. You start by plugging in specific input values, like assigning a 1 to A and a 0 to B. Then, you evaluate the gates in their dependency order. You figure out the first gate's output and feed that result straight into the next gate, cascading down step by step from input to final output. It's essentially executing the physical hardware right in your mind. But what if we flip it? Backward tracing goes in reverse. If I know my final output is a 1, which specific inputs made that happen? By consulting our truth tables, we can work backward. With 2 inputs, there are only 4 possible combinations. We can test them, map them out, and pinpoint exactly which starting inputs led to our desired outcome. It's kind of like playing detective, but with electrical signals.
Section 4. Adding bits, the half adder.
Meet the half adder. This is a logic circuit that takes 2 input bits and actually performs single-digit binary addition. And it gives you 2 distinct outputs, a sum bit and a carry bit. Think about when you add numbers on paper and you have to carry the 1 to the next column. Well, the half adder does exactly that, just in binary. This right here is where the math gets incredibly elegant. A half adder requires exactly 2 gates. That XOR gate we highlighted earlier, it perfectly computes our sum. Why? Well, 1 plus 0 is 1, 0 plus 1 is 1, but 1 plus 1 in binary is 0. Carry the 1. The XOR handles that zeroing out perfectly when both inputs are 1. Meanwhile, a simple AND gate sits right next to it, producing that carry bit, because you only ever carry a 1 when both input A and input B are 1.
Let's trace that bottom row to tie it all together. When inputs A and B are both 1, the XOR gate sees 2 matching inputs and outputs a 0 for the sum. The AND gate sees 2 1s and outputs a 1 for the carry. So our final output is carry 1, sum 0. Written out, that's a 1 and a 0 in binary, which is exactly how you represent the decimal number 2. With just 2 simple gates, we've literally taught electricity how to do math.
Section 5. Adding more, the full adder. Here's the catch with the half adder, though. It can only add 2 single bits. It has absolutely no way to accept a carried over number from a previous column. So to add larger numbers, we have to upgrade to a full adder.
The full adder takes 3 inputs instead of 2. It takes the standard bits A and B, but it also accepts a carry-in bit from a previous addition stage. This lets it seamlessly chain operations together.
With 3 inputs, our truth table expands to 8 possible combinations. The logic gets a bit more complex. The sum acts as a parity check of the 3 inputs, and a carryout happens whenever at least 2 of the inputs are 1. Now, by chaining these full adders together, letting the carryout of one flow right into the carry-in of the next, engineers create what are called ripple carry adders. These are the core multi-bit addition circuits humming away inside computer CPUs.
Section 6. Scaling up to CPUs.
Just look at that number, 64. When your computer runs a standard 64-bit integer addition, which is happening billions of times a second, it's relying on a continuous chain of 64 full adders. If you break that down into the individual AND, OR, and XOR gates we've been talking about, you're looking at a few hundred interconnected logic gates working together instantly just to process a single addition operation. Now zoom out to the whole chip. Modern CPUs contain billions of transistors organized into these gates. For more complex math, the architecture uses thousands of gates organized into highly specialized units. But here is the absolute mind-blowing takeaway. Every program ever written, every video game, every app, every massive software suite ultimately reduces to billions of these ridiculously simple AND, OR, NOT, and XOR gates just processing binary voltage signals. To wrap up this explainer, I'm leaving you with a quick challenge to test your engineering mind. If you're studying for the AP exam or just want to make sure this all clicked, for a half adder, if input A is 1 and input B is 1, what are the sum and carry outputs? Think back to our XOR and AND dates. Trace the logic yourself. It is truly amazing how these basic rules of logic, mapped onto physical electricity, construct the entire digital world around us. From simple ones and zeros comes infinite complexity. Thanks for joining me, and keep exploring.